Welcome to this video on continuity theorems. The theorems that we're looking at today are going to be useful in proving a function is continuous by stringing together a bunch of smaller functions that we know and can take as given as continuous. And then we'll also look at the Intermediate Value Theorem, which is a famous theorem that we use continuity for in practice that is also quite helpful and useful. Okay, so let's start off with our continuity theorems relating to proving a function is continuous. If you have two functions f and g that go from d to r and e to r, and we want to look at another function that's based off these functions here and look at inputs that are in the intersection of their domains, then these theorems here essentially say that f plus g as a new function, or f minus g, or f divided by g, or f multiplied by g, all of these functions are going to be continuous as well if f and g are both continuous. So this is actually really helpful because if you know that a simple function is continuous, you can then transform it using these transformations and know for a fact that that transformation is also continuous. So for example, you might want to prove x to the power of 5 is continuous. And what you could do is prove that x as a function is continuous, and then x multiplied by x multiplied by x multiplied by x multiplied by x is equal to x to the 5. And as the multiplication of continuous functions is continuous, so therefore is x to the power of 5. And that is a useful way and convenient way to show that functions are continuous. Sometimes you're looking at optimization context where you want to know that your function is continuous to use some theorem like the Extreme Value Theorem, and these theorems can be quite convenient to very quickly convince an examiner, for example, in an exam, that the Extreme Value Theorem is appropriate because the function is continuous because it is doing these things here. Okay, but often the standard continuous functions that we take as given as being continuous, which I have a list below of what is commonly accepted as being continuous, are in one dimension of input. And when you have two dimensions of input and you want to use a standard continuous function in one dimension, you need to take the projection to actually use it. So let me explain what a projection is. The projection function takes, if we zoom in here, takes an input x1 and x2 and then projects down onto the axes the value x1 or the value x2. You can imagine like shining a light down here onto x1 and x2, and then that will cast a shadow that projects down onto the axes here the value of just x1. And practically what that is doing is that it is extracting x1 from this vector into the projection of x1 and x2 that is just equal to x1. It looks more complicated than it is. It's just extracting one of these two values, x1 or x2. And that is useful because we can take a function in two dimensions and then extract the x1 input and put it into a one-dimensional continuous function, and then we can extract the x2 input and put it into a one-dimensional continuous function, and then show that they together stack up to be continuous overall. So in R squared, projection 1 just takes x1, projection 2 takes x2, and then for RK, projection I just takes xi, and that can be projection 6 if you had more than 6 dimensions. Okay, so the following is a list of continuous functions that are commonly used with the theorems above to build a more complicated function that's continuous, and that is a constant, so f of x equal to a constant, f of x equal to x, f of x equal to sine x, cos x, these trig functions, e to the x, ln x as long as your domain is 0 to infinity, square root x as long as your domain is 0 to infinity inclusive of 0, and the projection functions themselves. And these functions are all mapping from D to R, where D is a subset of R, In higher dimensions, we need to use projections to actually leverage the fact that these are continuous. Okay, so let's take a look at an example of that. If we wanted to prove that x1 squared plus x2 squared is continuous using continuity theorems, we could do something like this. First of all, notice that the projection I is just taking xi, and the projection I squared is going to be xi multiplied by xi, and then adding projection 1 squared plus projection 2 squared gives us x1 squared plus x2 squared, and that f is just equal to this. So f is equal to pr1 squared plus pr2 squared. That is the same thing as f. And now we can argue with our continuity theorems that f is behaving in accordance to those theorems. So the projection function is continuous. We know that is taken as given. We know that a continuous function times a continuous function is continuous, as the multiplication of continuous function is continuous. And then we know that the addition, the sum of continuous functions is also continuous, and f is equal to this, so therefore f is continuous. No conformity issues. This idea of conformity is that you can actually validly put into your stack of functions the domain, the output of one function into the input of another. So for example, if you had the square root as a function that you're looking at, and another function was equal to minus x, then that might produce a negative value overall. And then if you try to put that into the square root function, you might be putting a negative value into the square root function, which you can't do. It's not defined for negative values. And that would be a conformity issue. But there is no conformity issue here because this is a very simple example, and we're just addressing that at the end there. But this is something you should check for as you start stacking them, and definitely mention that there's no problem if there isn't one. Okay, so that's an example of using continuity theorems to show that something is continuous. Okay, the last thing we'll look at in this video is the intermediate value theorem. In practice, this is a very useful theorem. Let me first explain what it is mathematically, and then we'll look at it more intuitively. So suppose f is a function that maps from a to b in its domain to the real numbers according to some rule, and that this function f is continuous. Then for all u real number that is in between the minimum and the maximum of f of a and f of b, we know that there exists some c inside of the domain where f of c is equal to u. So essentially what this is saying is that if you look at your minimum value f of a and maximum value f of b, assuming f of a and f of b, no, let me re-say that. If you take your f of a and f of b values, then because your function is continuous, it had to get from f of a to f of b some way or another in a continuous fashion, and in doing so must pass through every c in between, every u in between those values. And if it's passing through every u in between those values continuously, then there must exist some c in the domain where f of c is equal to u. So let's look at that visually here. We've got a to b as our function domain here. We can calculate f of a here and f of b here. Then looking here, f of a to f of b, and we have every value in between our u. We know for a fact that there must be some c in between a and b, that f of c is equal to u. So let's just pick this one, for example. Then we can go across to our function, and then here we have this will give us, this is our c, that f of c is equal to u. And this must be true if the function is continuous. So practically we can use it by arguing, and by it I mean the intermediate value theorem, by arguing that 1, f is continuous on the relevant domain a to b, 2, here's what f of a and f of b are, and then 3, using the theorem we know that there exists some c in between a and b where f of c is equal to u. Most commonly this is used to prove the existence of solutions. So let's say you have a really intense optimization problem and you're not even sure if there exists a critical point. There exists a point where the derivative is equal to 0. What you could do is show that the derivative is negative in this region here, and the derivative is positive in this region here. And as the partial derivative is continuous, we know that somewhere in between those two options we just discussed, it must pass through 0, and therefore we can conclude a critical point exists. So yeah, the intermediate value theorem is very useful, and you often will get opportunities to use it in optimization contexts. All right, so that's all I have for these continuity theorems. I hope you find this video helpful. Thank you.